Okay, I guess we're rolling. The last of the Chapter 6 videos, chi-square test of independence, sometimes known as the two-way chi-square. I'm just going to flip-flop back and forth between those terms. You know what the one-way chi-square is now, so let's talk about the two-way. The two-way chi-square involves two variables. Shocker, instead of just one. And each variable has categories, so this is a test of association between two categorical variables. If one of your variables is actually a truly numeric variable, you probably don't want to use this. If one of your variables is something that can't be turned into numbers or categories, it's super weird, then you don't want to do this. Two categorical variables. Now, just like the one-way chi-square, the categories need to be mutually exclusive, but we need to say this a little more specifically since there are two variables, so two sets of categories. So each observation in the study will have a value for category, or a category or a value for variable 1, and a category or variable for variable 2. So each observation has to fit in exactly 1, not 2, not 0, categories on variable 1, and exactly 1 category on variable 2. So this is paired categorical data. Each observation has two values, but those values are categorical values, not numerical values like we talked about for, say, the paired samples t-test. And the categories can be ordered, or they can be fully categorical, like nominal categorical. And ordered is okay. And sometimes people take a discrete variable and chop it up into a few small chunks of ordered variables, like by ranges or something. It's not usually a good idea, but statistically, it's doable. This is sometimes called the two-way chi-square test of independence because the null hypothesis is independence of the two variables. The alternative hypothesis is that the two variables are associated, that there is an association between them. The very first thing we do before we get going on this is to set up a two-way frequency table. In other words, a contingency table. A contingency table between the two variables. And then the computation is fairly similar to the one-way chi-square goodness of fit, but the interpretation is different. And setting up the null hypothesis is different. So let's take this example. I've kept numbering from the last PowerPoint for some reason, so now it's example 4. Let's say you ask some students on a college campus what would happen, how would they feel if you increased tuition, and then later you ask how they would feel if you reduced the amount of parking on campus, or if they required you to start wearing uniforms to come to college. How angry would they be? So let's look at the increased tuition. Let's say each of these dots is an observation. So I'm trying to make this binning thing kind of visual. So this number of people said they'd have low anger if you increase tuition. This number of people said they would have medium anger if you increase tuition, and this number of people said they would have high anger. And then for reducing parking, a lot more high anger. Interesting. More. I think these are data from an actual study that was done about 10 years ago or so. So I think it's reported in one of our textbooks, maybe the textbook we have right here, so I'm going to be embarrassed if it's in there. Well, what are you going to do? And so high anger if they reduced parking, and medium anger if they required uniforms. So looking at this, what can we tell? Are these variables dependent or independent of each other? Conceptually, you need to ask yourself the question. When you look at one variable, pick any variable. So does the level of anger that a person has, or the pattern across categories, the pattern of anger that a person has, does that depend on the particular policy change? You could also say, does the pattern of responses across policy changes depend on the level of anger? But statistically, they're equivalent. You can say either one of those. But it actually makes a little more sense kind of conceptually to say it the other way around. Does the pattern of students' anger in their responses depend on the particular policy change that's being suggested? And we can draw lines here. So we could draw a line to show us kind of like the tops of the bars, the tops of the dots for increasing tuition. The pattern of anger stays more or less the same and then drops. There aren't very many people high. There's a medium amount of low and mediums, and then there's not so many high anger people. And then down here, for reducing parking, the pattern just goes up. It's mostly high anger and not so much anger down here. And then for requiring uniforms, you have mostly medium anger. So these patterns don't appear to be the same. In other words, your pattern of anger does depend on the policy that's being talked about. It depends on that. And that dependence is association. In other words, it's just as valid to say the hypothetical anger that students would experience is associated with the policy change that's being suggested. Now, if there was no association, we would expect these lines to be perfectly parallel to each other. They can have bends in them, they can be zigzaggy, but it has to be the same zigzag for this line as this line as this line. And so you could think of the chi-square independence test as a test of how non-parallel the lines get. And they have to deviate from parallel a certain amount before you can say that's enough deviation that we trust that that they're not parallel in the population too, not just in our sample, that the unparallel exists also in the population. So the unparalleledness is association, as weird as that seems. But if you work through it, I think you'll see that it works. So the research questions we ask are, does variable A depend on variable B? Or more specifically, we might say, on average, does your typical observation, does the typical observation's category on variable A depend on that observation's category on variable B? Is there dependence, statistical dependence? You could rephrase it in statistical terms. If you were to try and guess a person's value, which category of a person or an observation falls into on variable B, does knowing their category on variable A help you predict that? These are all equivalent. Non-parallel lines, probability of the category on variable A influencing the probability of category on variable B, knowing something about variable A category helping you predict variable B category, variable A depends on variable B. These are all the same thing. These are ways of talking about association. Now when we get with numerical variables, we will call that correlation. But right now we're going to stick with association, a more general, vague term, because that's what's happening between these categorical variables. Now, if the observations do depend on each other, if the binning of variable A depends on the binning pattern of variable B, then variable A and B are not independent. They are dependent, they are associated, whatever. So when we do hypothesis testing, it's the same as before. We state the null and the alternative hypothesis. Drawing a diagram isn't going to be very helpful because you're going to draw a diagram of the chi-square distribution, which doesn't help very much. It doesn't really help you visualize the problem in my experience. But you are going to look up the chi-square critical value, state your rejection rule, like under what circumstances will you reject the null hypothesis, calculate your observed chi-square value, state your decision about the null hypothesis, and then state your conclusion. So let's just do examples. Let's say that the juvenile justice system in a large city gives 4 educational programs for at-risk youth. Do the different programs have any differential effect on youth crime? Now, when you become a super savvy stats person, you will look at this and you'll think for a couple minutes and you'll say, this sounds like they're talking about association. Now, if they're measuring with numerical variables, maybe we're going to be looking at like a t-test or an ANOVA or regression and correlation. But if they're measuring with all categorical variables, we're definitely looking at the chi-square test of independence. So another way to say this is the type of program related to or associated with later commission of crime by the students. And let's say alpha is 0.01. So let's assume, and you'll see in the next slide this is true, that both variables involved here, commission of crimes later, and then the particular program you're in, these are both categorical variables. So then the null hypothesis becomes the two variables are independent of each other. So the commission of crime later, your probability of committing a certain crime or your level of committing crime is independent of which program you went to. The alternative hypothesis is that they are actually associated with each other. So keeping that in mind, does the number of crimes committed by a young person depend on the program that the person attended? Here's the data. So this variable, the variable in the columns, is the number of crimes committed. And you can see the number of crimes. Overall, a lot of people committed no crimes, fewer people committed one crime, and a very few people committed more than one crime. And then over here we have the programs. Let's say there's 4 separate programs. And we had roughly equal enrollment in the programs. It's around 200 for each. And so you can look at the numbers here, and it might be kind of hard to make sense of them. One of the things we can do to make sense of them is we can graph them. When you have this kind of a situation, why are we not advancing? There we go. I hope we don't advance too much. When you have a situation with these two variables like this, one way to graph them is with a bar chart, a clustered bar chart. So the clusters, the x-axis will be one variable, and then the cluster groups will be one variable, and then the specific bars within each group will be the other variables. So in this case, I'm putting the program on the x-axis and I'm clustering it by the number of crimes. So you can see program A had, a lot of people committing 0 crimes, fewer people committing 1, and then a very few people committing more than 1. Program B looks similar, except even more people committing 0 crimes. Program C, they got a lot of people committing 1 crime. Their 0 crimes is kind of similar, but they've got a lot of people who should have been in 0 crimes have been kind of moved down here, and they're in the 1 crime category. That's not good. This is a more criminal category. It's not as effective or maybe it's actually teaching people how to be more criminal. And then program D, you're just screwed, man. There's a whole lot of people come out of program D who commit a crime. On the other hand, they're not committing a lot of crimes, not more than 1 crime, just 1 crime. Now you can try and imagine connecting the tops of the dots here. Oops, let's go back here. You can imagine connecting the tops of the dots here and making some lines and deciding whether these lines are parallel or not. So hang on. Okay, I think this is going to work. Let's try and connect the tops of these lines here. Oops. Can I draw here? Okay, let's connect the tops of these bars, and that's kind of the pattern across the programs. Now keep in mind the order of the programs is arbitrary, so this pattern is not written in stone. We could rearrange the programs, but we're just going to see if things are parallel. And then this one, the second bar, the bar for 1 crime. When the lines cross, that's a bad sign. That usually means something's going on. And then those really don't look parallel to me. That's going to make me guess. That crazy non-parallelness, I'm going to be leaning towards there's going to be some kind of an effect there. Now we could also plot this the other way. We could put the number of crimes on one axis and then cluster by programs here. And that might give you a different view of things. So here you can see program A, program B is kind of the leader in no crimes. Program D is the leader in 1 crime, and then program C is the leader in more than 1 crime. So you could also do, let's see, pointer options, the pen. You could also do that connecting things here. And so you can see that program A, that we're just basically redoing what we saw from program A last time. And then this is not the same pattern, and then that's really a disturbing pattern there. So we see some non-parallelness, parallelation, I don't know. Anyway, let's do the numbers. You compute the 2-way chi-square. You're going to do the same thing as before. You're going to calculate observed minus expected for every cell in the table, for every frequency in the table. Now, if you're using proportions or percentages for one variable, like the observed variables, they might need to be converted to frequencies on the same scale, kind of like we did for the 1-way chi-square. The expected values are not based on the null hypothesis that you create anymore. That's how this is really different from 1-way chi-square. The expected values are based on the numbers that are already in the table. You don't usually generate any null hypothesis of any kind. The null hypothesis comes from the values in the table, because the null hypothesis is that things are not associated, and that's purely dependent on the values themselves, not dependent on a particular hypothesis. So you get the expected frequency based on the values from the rest of the table, and the degrees of freedom are calculated as the number of rows minus 1 times the number of columns minus 1. I better fix this pointer here. So rows minus 1 times columns minus 1, and we'll see how that works. So the expected frequency for any cell, it gets a little computationally intensive with a big table. It just takes a long time. It's the column total, the marginal total, the total that's down in the margin or over in the margin, the column total at the bottom times the row total. And that's for each cell. And then for each of those, you divide it by the total ends. So it's like the expected proportion of column times row, something like that. And so what that gives you is the proportion or the number of observations that should have been there if there was no association between the two variables. And you repeat that for all the cells. So the expected value for a particular row and a particular column, I and j, is the row total times the column total divided by the n for the entire study. Looks complicated, but it's actually pretty easy to do. It's just kind of a pain. So we can get our data back up here again, program A, B, C, and D, and you've got your row and your column totals. So here, the expected value, 115.68, is going to be 200, which is the row total, times 461, and that's going to be, 8 bazillion thousand, whatever. And you'll divide that by 797, and that'll give you 115.68. Again, this one here, 73.27, is going to be 200 times 292, and then that total divided by 797. And the expected value of 11.04 for the column for the cell with 8 is 200 times 44 divided by 797. So you can see that this is matching up pretty closely in this particular case. We're getting pretty close for program A. Program B looks fairly close, but the 3971, that's kind of a deviation there. And then program C doesn't look too terrible. Program D, oh, they've got a bit of a problem there. That's like 30 difference. So it's going to be a big difference. So we can figure out for each cell, observed minus expected squared divided by expected. This is the same as the one-way chi-square. And so we can get those values. So observed minus expected, that, squared divided by that. So 122 minus 115.68, whatever that turns out to be, square that, divide it by 115.68. This is a very small value. So this chi-square component is 0.34. This is small, 0.15, 0.84. Now this is big, 14.73, and that's that big difference right there, one crime for program B. It's not what we would expect it to be given the rest of the values in the table if they were independent. And then this is huge down here too, 13.26. It's one crime for program D. And then you just add all these up, and that's your chi-square. In this case, if I did things right, it turns out to be 54. So the calculations are kind of a pain, and it takes a while, and you have to kind of keep some things straight in your head. But you don't have to do calculus or anything weird. You don't even have to do a square root. You're just adding things and squaring things and dividing things. You can do this on the calculator you got from the bank, the one that doesn't even have a square root thingy on it. So the critical chi-square, we looked that up in our table in the back of the book. The degrees of freedom is 6 because there are 3 rows or 3 columns, minus 1 is 2, and 4 rows, minus 1 is 3. So 2 times 3, 6 degrees of freedom, and we decided alpha is 0.01. So the critical chi-square is 16.81. We got to beat that. We got to have a number higher than that. And our chi-square observed is 54. That's a lot bigger than 16 or 17. So observed is greater than critical, therefore our p-value is less than our alpha value. So the probability of observing this, if the null hypothesis is true, is less than our type 1 error benchmark rate. So we reject the null hypothesis, and in conclusion, the two variables are not independent. The null hypothesis was that they are independent. In other words, now the pattern of commission of crime does depend on which educational program the juvenile attended. We reject the idea that it doesn't depend, that those two variables are not associated. So our next step would probably be to do some one-way chi-square tests, and possibly then some proportion tests for 2 particular cells at a time, with selected subsets of values. You'd pick certain subsets of values to test, like a certain row or a certain column, to do a one-way chi-square on, or 2 cells right next to each other to do a proportion test, until you kind of zero in on where the differences really are, so you can pinpoint which of these programs is doing well, which is doing poorly, and what are the strengths and weaknesses. I can tell you there are a couple of programs that aren't doing very well in the whole people commit one crime after they leave your program area, and so that's what I would focus on if it were me. So just to go over the terms here, sometimes you'll see tables like this with parentheses. Parentheses numbers in tables can mean a lot of things, but if it's a chi-square thing, sometimes these are the expected values, the expected frequencies. That's the margin totals, the totals in the margin. It's just adding up the actual values. 15 and 10 is 25, etc. So let's look at another example. Do women and men differ in their support of regulation of firearms? Let's say there's a survey with N of 100 people. and let's say the question was, do you think people buying firearms should be required to undergo a background check, like as a condition of buying the firearm? Let's say these are the answers. Yes, no, and some people were allowed to say maybe. Women and men. So first of all, I'd graph these using clustered bar charts. And then I would crank it out and do the calculations. So the hypotheses we're going to be working with is that those two variables are independent. So support for firearms and the participant's sex. So our research question could be, do men and women differ in their support of firearms regulation? Or it could be, is support for firearms regulation related to a person's sex, or is it associated with a person's sex? One of those two things. Did I say alpha equals 0.05? Apparently so. So the alternative hypothesis is that they are not independent. In other words, by default, that they are associated. So the observed values will be different from what we would expect. An expectation is expect if the null hypothesis were true. Here's one way we could graph that data. Putting sex as the clusters on the x-axis, and then the values within the clusters could be the response values. And this is the way I prefer, honestly. So men, you've got this many saying yes, this many saying no, and this many saying maybe. Women, you've got yes, no, and maybe. Different patterns. So these kind of form non-parallel lines, making me think that there's at least a chance that the chi-square will not be significant. Okay, my phone got in the way there. So that's not really parallel to this, and we've got some chance for things to not be significant here. We could graph it the other way too. We could put yes, no, and maybe on the x-axis and cluster them by, or within the clusters put separate bars for men and women. So you can see men's pattern is this, and women's pattern is this. I don't know, that's not that different. It's a bit different. I mean, visually there's a difference. The question is, with an n of 100, is that statistically significant? Is that enough for us to trust that that difference in pattern is also present in the population? So let's look at the numbers here, and let's put some expected values in there. Here we go. 40 times 50, that's going to be 900. Sorry. Yeah, I know what I'm doing. Oh, I know what I'm doing. All right, 40 times 50 is going to be 2,000 divided by 100. That's 20. So we're figuring out our expected values here, and these are going to be the same because there's 50 and a 50 here. You're always going to be getting the same division. This is going to be multiplied by the same thing for both cells here in the columns. Anyway, it works out that way when you have equal values on one of the variables in one of the categories. So those are our expected values, and then working out the chi-squared components, they work out to be fairly small. You should look at those, they're all less than 1, and think, oh, this doesn't look good for dependence. Looks pretty good for independence. Chi-squared is 2. That's pretty small, 2.07. So the critical chi-square, there are 2 columns, and so 2 minus 1 is 1. And there's 3 rows. 3 minus 1 is 2. So 1 times 2 is 2. So this is a 2 degrees of freedom chi-square, alpha 0.05. So similar to what we had before. Critical chi-square is 5.99. Our observed chi-square is much smaller. So observed is less than critical. Therefore, p is greater than alpha, which is bad. We fail to reject the null hypothesis. So the conclusion is that the evidence does not suggest that support for firearms regulation and sex are associated in any way. So whether you support firearms regulation kind of has nothing to do with whether you're male or female, as far as we know from this data. So there's not enough evidence to suggest that there's any link. The pattern of support for firearms regulation does not seem to depend on sex. We retain the hypothesis that it's independent of sex. On the next step, we don't do anything. We stop. This test was not significant, so we don't move on from here. We say there are no effects. And once again, that's a way we protect ourselves from doing too many tests. Feel free to pause and digest and go back and look at the values there and my crazy squiggles. But I'm going to move on here for another example. From the Monitoring the Future study, you have this data available on my website, MTF 2006. I thought it would be interesting to look at the subjective importance to each student, these are high school students, of money. The question was, how important is it to have a lot of money, with some categorical answers. And then the expectation that other people would be fair. Do you think most people would take advantage of you if they had the chance, or would they try to be fair? And there are some categories for that too. You'll see in a minute. So the null hypothesis is that students' expectation that other people will be fair is independent of the importance of money to them, to the students. And let's say alpha equals 0.01. The alternative hypothesis is that the expectation of fairness does depend on the subjective importance of money. So here are what the data work out to be. So here's the expectation of fairness. If they had the chance, other people would. They had three choices. Do you believe other people would take advantage of you? You don't know, or you're undecided, or they would try to be fair. And then the subjective importance of money to you. Not important, somewhat important, quite important, extremely important. So these are categorical variables, and these are the numbers. There's the marginal totals that you got going on there. It's a big survey, and so there's 2,400 students, high school students who answered this. I believe it's high school students. So we could graph this by putting the responses on the x-axis and clustering, or the responses for fairness on the x-axis, and clustering the bars in clusters where each cluster has a range of the importance of money to each person. So let's look at money not being important. That looks almost flat. Let's look at money being somewhat important here and here, and then it kind of drops a little. That's pretty parallel. That's really parallel right there. Let's look at money being quite important. Oh, that's different. That's not parallel. And with an n of 2,400, even small differences, deviations from parallel lines, are probably going to be statistically significant. 2,400 is a big n, and even small differences will be significant. And then quite important is this. So they're not totally parallel, but the two top ones drop quickly, or have a big difference between take advantage and try to be fair. And the two lower important categories don't have a big difference between those. Another way to look at this is cluster them the other way. So put the importance marching upward on the x-axis and cluster that by, for each level of importance, what do you think other people would do? So do you think they would take advantage? As the importance increases, the probability of thinking that the other people would take advantage goes up and then drops down again. The probability of saying you're undecided goes up and then drops down again. And then the probability of saying the other people would try and be fair goes up and then drops very quickly and stays flat. So I think, honestly, this is where the difference is going to happen. Well, this region right here is where the difference is going to happen. I'm just going to make some more circles to make this slide as messy as humanly possible so you can't understand anything from it. Let's just move on. So let's look at these expected values. We got those by multiplying this times this, dividing by this, and that gives us 64.15. So we can see these deviations here, the expected values. They're not huge, but they're there. And then we can look at the chi-squared components. So this is observed minus expected, squared divided by expected. And we can see there's kind of a big difference here. There's a fairly big difference here, fairly big difference here, and slightly biggish differences in some other places. I'm not very good at writing circles with my mouse. So somewhat, people who thought money was somewhat important, they were a little off in thinking of how likely people would be to take advantage of you. They were off from what they should have answered, or the number of people who should have answered this if the two variables were not associated. And here we're seeing another piece. This is something we wouldn't expect if the variables were not associated. People thinking money is somewhat important, trying to be fair, probably because these just had a trade-off between them. And then quite important, the number of people who think you would try to be fair. So you can kind of see that there's going to be some differences there. And remember, an n of 2,400, it's gigantic. So the critical chi-square, 2 times 3, because there's 3 columns and 4 rows, so 2 times 3, 6 degrees of freedom. Alpha is 0.01, 16.81. Well, it's not there. So the n didn't really matter in the end. It probably would have been significant at chi-squared, or at alpha equals 0.05, but there wasn't enough of a deviation from those parallel lines, or from what we predicted, to say that there was dependence between those two things. So, at least at the alpha is 0.01 level, chi-squared observed is greater, sorry, that's really bad. Hang on, let me fix that. Alright, let's try this one more time. Chi-squared observed is less than critical, therefore P is greater than alpha. Oops. We fail to reject the null hypothesis. Check out that magic. And in conclusion, the two variables seem to be independent of each other. Or we could be more technical in saying there's not evidence, the evidence does not suggest that there is any dependence. The null hypothesis that they are independent is what we have to retain. We can't reject that. The data don't give us evidence to reject it. So the pattern of expecting fairness in other people does not seem to depend on how important money is to you if you're a high school student in this study. So the next step, we do nothing. We don't do anything else because we're done. This shouldn't say number 1 anyway. So I'll finish with this lecture. Sorry it took so long, but this is complicated stuff. I'm sure it doesn't seem as complicated to you now, and that's as it should be. If it still seems crazy complicated, watch this lecture like 20 more times and do all the examples in the book. And come see me in office hours.